Look deep into the night sky, beyond the familiar constellations, beyond the glowing clouds of cosmic dust, and past the billions of shining stars that make up our Milky Way. The universe appears to be a landscape of light. But this light is a deception. Lurking in the dark, silent corners of the cosmos are entities of such extreme violence and incomprehensible power that they bend the very fabric of reality to their will. They are the ultimate cosmic apex predators. They consume planets, they tear apart stars, and they even swallow light itself. Today, we are journeying into the most terrifying and mysterious objects in the universe. Black holes, the ultimate cosmic predators. To understand a black hole, we must first understand how a star dies. For millions or sometimes billions of years, a massive star exists in a delicate state of balance. Deep within its core, a relentless nuclear fusion reaction pushes energy outward. At the exact same time, the crushing, unimaginable gravity of the star's own massive weight pulls inward. This balance between outward radiation and inward gravity is what keeps a star stable. But fuel is not infinite. Eventually, a massive star burns through its supply of hydrogen, then helium, and finally begins fusing heavier elements until it creates a core of solid iron. Iron does not release energy during fusion. It absorbs it. The delicate balance is instantly shattered. With no outward pressure to fight back, the absolute weight of the star crashes inward at a significant fraction of the speed of light. The star collapses on itself, resulting in a cataclysmic explosion known as a supernova. But what happens to the core left behind? If the dying star is massive enough, at least 3 times the mass of our own Sun, the gravitational collapse does not stop. It cannot stop. The gravity is so powerful that it crushes the iron atoms. It crushes the protons and electrons together. It crushes the very empty space inside the atoms. A mass greater than several of our suns is squeezed into a sphere the size of a small city, and then it is squeezed even further until it becomes infinitely small. A hole is torn in the fabric of space-time. A stellar mass black hole is born. The anatomy of a black hole is unlike anything else in physics. Because it is completely dark, we cannot see the object itself. We can only see the chaotic, violent environment that surrounds it. As gas, dust, and ripped-apart stars are pulled toward the black hole, they do not fall straight in. They spiral around it, moving faster and faster, creating a flattened, glowing disk of superheated plasma. This is known as the accretion disk. The friction inside the accretion disk is so intense that the gas heats up to millions of degrees, glowing with blinding X-ray radiation. It is a swirling hurricane of fire, illuminated by the dying screams of shredded stars. But if you look past the glowing disk, toward the center, the light simply vanishes. You reach the boundary of the abyss. This is the event horizon. The event horizon is not a physical surface. It is not a wall. It is a mathematical boundary, a sphere of no return. To escape the gravitational pull of any object in the universe, you have to reach a certain speed. To escape Earth, a rocket must travel at roughly 11 kilometers per second. This is our escape velocity. But as you get closer to a black hole, the gravity becomes so intense that the required escape velocity rises exponentially. Exactly at the boundary of the event horizon, the escape velocity matches the absolute speed limit of the universe, 299,000 kilometers per second. The speed of light. Because nothing in physics can travel faster than the speed of light, absolutely nothing can escape once it crosses this line. No rocks, no spaceships, no radiation, and no light. The event horizon is the ultimate veil of censorship. Whatever happens inside stays inside forever. But what if you could survive the journey? What if you were falling toward the event horizon? What would you experience? Here, the universe reveals how truly bizarre it is. Because of Albert Einstein's theory of general relativity, we know that massive objects warp both space and time. This phenomenon is called gravitational time dilation. If you were falling toward the black hole, and I was watching you from a safe distance in a spaceship, we would experience two completely different realities. To you, the fall would seem normal. You would look ahead at the encroaching darkness and look back at the universe shrinking behind you. But from my perspective on the spaceship, something horrifying would happen to you. As you got closer to the event horizon, the extreme gravity would slow down time itself. I would see your movements become sluggish. It would take years, then centuries, for you to wave your hand. As you reached the very edge of the event horizon, time would appear to stop completely. The relativity of time. To the outside observer, you would freeze, perfectly preserved at the edge of the abyss, slowly fading to red as the light stretching away from you lost its energy. I would never actually see you cross the threshold, but you would cross it. And once you passed the event horizon, you would encounter a horrific physical phenomenon caused by the extreme curve of gravity. Because the gravity increases so drastically over such a short distance, the gravitational pull on your feet would be millions of times stronger than the pull on your head. This difference in gravity would stretch your body perfectly straight, pulling you like a piece of cosmic taffy. Astrophysicists actually have a technical term for this violent, agonizing death. They call it spaghettification. Your body would be ripped into a stream of individual atoms, plunging deeper into the dark. Where do those atoms go? They fall into the absolute center of the black hole, a place where the laws of physics simply break down and cease to exist. The singularity. According to our current equations, the singularity is a point of infinite density and zero volume. All the mass of the original star, plus all the planets, gas, and light it has ever consumed, is compressed into a single, dimensionless dot. Space and time are curved to infinity. It is a mathematical error in the code of the universe. We currently have no physics capable of describing what truly happens here. And the monsters only get bigger. The black holes formed by collapsing stars are relatively small. But lurking at the center of almost every large galaxy in the universe is something far more terrifying. Supermassive black holes. In the center of our own Milky Way, 26,000 light-years from Earth, sits Sagittarius A star. It is a sleeping giant containing the mass of 4 million suns. But even Sagittarius A star is a dwarf compared to the true titans of the cosmos. Deep in the distant universe lies an absolute behemoth known as TON 618. It is one of the largest single objects ever discovered. Its mass is not measured in millions, but in billions. TON 618 contains the mass of 66 billion suns. Its event horizon is so unfathomably massive that it would swallow our entire solar system 11 times over. It is a gravitational abyss so deep that it anchors an entire quasar, shining with the brightness of 140 trillion suns. For decades, Scientists believed that black holes were eternal. They believed that once matter and information fell inside, it was locked away until the end of time. A black hole would only grow larger, darker, and colder. But in the 1970s, the brilliant physicist Stephen Hawking realized something groundbreaking. He applied the laws of quantum mechanics to the edge of the event horizon, and he discovered that the universe is never truly empty. Empty space is constantly boiling with pairs of virtual particles, matter and antimatter, that pop into existence, collide, and destroy each other in a fraction of a second. But Hawking theorized that if a pair of these particles appeared exactly on the boundary of the event horizon, something impossible happens. One particle gets sucked into the black hole, while the other particle is flung out into space. Hawking radiation. Quantum evaporation. Because the black hole gave up energy to separate these particles, it loses a microscopic amount of mass. This means black holes are not completely black. They glow, very faintly, with radiation. And more importantly, it means they are slowly evaporating. It is a painstakingly slow process. It will take a supermassive black hole a googol of years, a 1 followed by 100 zeros, to completely evaporate. But eventually, in the deep, dark future of the cosmos, every single black hole will shrink, violently explode, and vanish. This brilliant discovery solved one problem, but it created the greatest crisis in modern theoretical physics. If a black hole evaporates completely, what happens to everything that fell inside? What happens to the planets, the stars, the books, the civilizations, and the atoms that were swallowed? The information paradox. A fundamental law of quantum mechanics states that information cannot be destroyed. The universe must always keep a record of what things are made of. If you burn a book, the information is not lost. It is just scrambled into smoke and ash. With a powerful enough computer, you could theoretically rebuild the book. But if a black hole swallows that book, crushes it into a singularity, and then evaporates into random, featureless Hawking radiation, the information is gone, erased from reality entirely. This is the information paradox. If black holes destroy information, then the most fundamental laws of quantum physics are wrong. If quantum physics is right, then our understanding of black holes is completely flawed. To solve this, physicists have proposed a mind-bending idea. What if the information of everything that falls into a black hole never actually makes it to the singularity? What if, as an object crosses the event horizon, its three-dimensional information is smeared and perfectly encoded on the two-dimensional surface of the event horizon itself? The Holographic Principle. Information is encoded. When the black hole evaporates, the Hawking radiation carries this encoded information back out into the universe. The book is not destroyed. Its quantum signature is just stored on the surface of the black hole like a cosmic hard drive and eventually released back into the void. This principle suggests a staggering possibility. If the three-dimensional interior of a black hole is just a projection of information stored on its two-dimensional surface, could our entire universe be the exact same thing? Are we living in a three-dimensional projection of a two-dimensional reality? Black holes are not just cosmic vacuums. They are the ultimate laboratories of the universe. They are the places where time stops, where space is crushed, and where the deepest secrets of quantum mechanics and gravity are hidden. They challenge our perception of reality, reminding us that the universe is far stranger, far more violent, and far more beautiful than we could ever imagine. Keep looking up.